Modern physics. As always, if you enjoy this content, give us a like and subscribe. So the first part one of the modern physics unit, I am going to basically tell the story of how we get up to the Bohr model of the atom. But in the Regents curriculum, a lot of what I'm going to cover here is the backstory, and it doesn't get tested. Now, I encourage you to follow along with this. But if you really are only concerned with your grade, part 2 is where most of the questions are centered. So modern physics really starts with the Greeks. And what they were wondering was what stuff is made of. In other words, what are things, objects, stuff, everyday stuff that we have in our world, if we chop it up, what's the base level of what it's composed of? So the Greeks had this word, and the word is atomos. And atomos, in Greek is not, and tomos is cut. So the Greek idea of atomos is that something can't be cut. It's indivisible. So what they did was they had no experiments to back up this idea. They said that if you take an object, like let's say a piece of metal, and you cut that piece of metal in half, and then you cut that in half, and you continue to do that, you'll eventually get to these little particles that can't be cut, and these little particles are called atoms. So it wasn't until the early 1800s that a guy came along called John Dalton. And John Dalton was a chemist, and what he did was he developed a method for determining atomic weights. So what this meant was that he could take elements and figure out the weight of each one. So what he said was that matter or stuff is made up of little spheres, and that these spheres are indivisible. So you'd have a little chunk, and that little chunk would be hydrogen, and that's it. You can't chop it up anymore. And helium, the next element up, would just be larger. It weighs more. And lithium, and so on, so that the whole periodic table would be made up of these little individual spheres. As the size goes up, so does the mass. So nothing really happens with Dalton's theory. Nobody advances this theory until J.J. Thomson comes up in 1897 and does this experiment that has a new explanation for what atoms might be. So what he does is he takes a voltage power supply and hooks it up to a metal plate and a second metal plate that has a little tiny hole in it. So he puts both of these inside a vacuum tube. So this is just a glass tube, and all of the air is pumped out. So there's nothing in here except these two metal plates. And then he turns the voltage on. So we know from the electricity unit that that side is negative and this side is positive. So what he ends up observing is this beam comes out. And this beam goes all the way along, and this was actually the invention of the first television. And there's a little coating here where he could see where it hit. But with the lights off, you can actually see this beam. So he didn't know what this beam was. But you have a negatively charged plate here and a positively charged plate. So it seems that something negative is leaving this plate and being attracted to this positive plate. So the first thing that he did was he took a metal plate on both the bottom and the top, and he made the top negative and the bottom positive, and what he noticed was that the beam bent. So the beam went down like that. So what does that tell us? Well, it tells us that this beam must be negative. But he wasn't 100% sure. So the next thing that he did was he put a magnet around it. And whether, depending on the orientation of the magnet, he took a horseshoe magnet like this, so that that came up and then it's going up on the other side. And he had the south and the north poles, and he noticed that when the beam came through, it ended up diverting and curving. Now, everybody knew at that time that if you moved an electric charge, that would end up producing a magnetic field, so it made sense that this beam would curve if it was made up of negative charges. So he comes up with this idea and says that this beam must be the flow of little tiny electrical charges. So this is the discovery of the electron, these little tiny negative particles. But here's the problem. What are they? Because now we have these little negative things. So we have the atom, which is supposedly this indivisible sphere. So what he says is that maybe what these atoms are made up of are the little electrons that he discovered embedded inside this material that is positive. So there's this positive junk, like, that the electrons are embedded in. So you could think of this sort of like a chocolate chip cookie. Now, he used plum pudding because in England that was a type of food they would have at holiday times, and they would take plums, actually currants, a type of raisin, and put those inside this pudding. So he was saying that the gooey parts was positive, and the little negatives, which are the electrons, were embedded inside of this. So this becomes the plum pudding model. Now, why is this a big deal? It's a big deal because it's the first time since the Greeks and Dalton that somebody advanced the idea of what the smallest things are made out of. So now the idea of a neutral small chunk is made up of little negative and positive bits. So after the discovery of the electron and this plum pudding model, there's a guy named Rutherford who does this experiment, which ends up advancing the theory of the atom even further. So he's got some lead here, and inside the lead, he's got a piece of radium, which at the time was known to be radioactive and was known to eject positive particles. So he's got this positive stream of particles. And what he does is he makes a little hole in a piece of lead so that he can concentrate this beam. And then he sends this beam through, and this is gold foil. If you remember from chemistry, that's AU. So what he expects is that this beam of these heavy positive particles are just going to go cruising through, and then here he puts a ring, and this ring has photo paper, like a type of paper that when it gets exposed to this beam, it ends up leaving a mark. So he actually had this extend all the way around like that, but for my drawing, I'm just drawing part of it so you can see it. So he expects these positive particles to go cruising through and hit the other side. But what happens is most of them go through, but every once in a while, one of them gets curved. It's like 1 out of a few thousand or something like that. So if they get curved, some of them actually bounced back and hit the photo paper back here. So that's super crazy because we're thinking that this atom is made up of this plum pudding with the electrons spread out. So we would think that these positive particles should be able to just pass straight through as they have with other materials. But now some of them are bouncing back. So we can see here that we have our nucleus in the center, and these are the alpha particles, the positively charged particles that are traveling through the gold foil, and most of them you can see just go straight through, but the ones that get close to the nucleus
get deflected. In other words, they're sort of bouncing or being pushed around. So if we look at this, here is the planetary model. The little purple dots represent the alpha particles, and the little yellow dots represent the nucleus, and we can put some more in here. And you can see that we're still getting this deflection, which tells us two things. The nucleus is very dense, and it is positively charged.
So what does that tell us? Well, he concludes that there must be a small, dense, positive nucleus. So he's saying that now, instead of having this positive gunk all spread out, that there must be a positively charged particle that is in the center, or at least a combination of them. And then instead of having the electrons sprinkled about, he says maybe it's like the sun. And the electrons are orbiting around this nucleus, just like planets around the sun. So this ends up becoming known as the Planetary Model, and this is an advancement. So we start out with the Greeks with just a small sphere, and that's what Dalton talked about. Then we get this plum pudding model of little things embedded, and then we get this planetary model, which is closer to what we already know now, which just growing up or going through middle school, you learned about this model, but we're going to find out it's a little more complex than that. So if we take a very cold black object, it will not emit any light. Now, when we say light, we're talking about all electromagnetic waves. So ultraviolet, infrared, gamma, the works. So by a very cold black object, we could think of the coils inside of an oven. Those coils are going to be enclosed. They're going to be black. They're not emitting any heat. So therefore, this object is called a black body. So this is going to be the idea of black body radiation. And the theory of black body radiation says that when you take an object and you start to heat it up, it will start to produce light in higher and higher frequencies. So just think about your own body. Your own body is hot. It gives off infrared radiation. So you can't see the heat. It's not red. It's not in the visible spectrum. But if you hold your hand near your ear, for example, you can actually feel the heat being reflected back. But as the temperature of the object goes up, the higher the frequency of the emitted waves. So we know that when we have a light bulb, if we just turn on the light bulb a little tiny bit, not enough to light up, the light bulb, the filament, you won't be able to see anything coming out of it yet. That will be a black body. But it is emitting some waves, low frequency waves, that's infrared. And if you touch the bulb, it's warm. But if you start to heat up the filament and put more voltage through it, it will continue to get hot, but it will also start to glow red. So at this point, the filament will be red. But if we continue to heat it up, we'll start to get higher and higher frequency waves. So now we're getting red and infrared and orange. So now it will start to glow orange. And as we start to add more, we eventually get yellow, green, orange, red, infrared. This combination will give us yellow. And then finally, if we get it to emit all of the different frequencies, red, orange, yellow, green, blue, violet, and infrared, we can't see the infrared, but what's the combination of Roy G. Biv? That's white. And that's why when we say something is white hot, it's emitting all of the different frequencies of the visible spectrum. What happens if we continue to heat it? Then we will get even ultraviolet, which is a black light. And at a high enough frequency, this actually starts to become dangerous.
Here we can see the object acting as a black body. As the temperature goes up, it heats to red, then to orange, yellow, and eventually to white as the frequency goes up.
So we know that these black bodies are black. They absorb all the frequencies when they're cold. But what happens if we start to heat them up? Now, a star, like the sun, acts as a perfect black body because when it's cold, we would not see anything. We would have no sun. It would just be black. But because the sun is very hot, it ends up producing all of the different frequencies of light. And if you graph all of the different frequencies, you get a curve that looks like this. So most of what we get, this is the curve of what it would look like at about 5,000 Kelvin. So from the visible spectrum, that's what we get the most of. And that's why our eyes evolved to be able to see in the visible spectrum. But then as we move further along here to larger wavelengths, we get less. And here's the tricky bit. It starts to decrease on the other side. Now, why is that the tricky bit? The tricky bit is because there was a model that graphed intensity as a different graph than what the experiment came out to. And this was equal to a constant, which I'll just put in times K, times the temperature divided by lambda to the fourth power. Now, you don't need to know this formula, but the idea is this, is that if you graph it, it matches the graph that we observe from the sun, from a black body radiator, but then it just continues to go up and up and up, saying that as the wavelength gets smaller and smaller and smaller, that the intensity would just go up to infinity. And the experimental data did not show this.
So here's our blackbody spectrum. And if you look over here, we can change the temperature. So we're down at very low temperatures, and this graph gives us the wavelength and the intensity. And as we start to increase the temperature, you can see that we start to produce light, actually all the electromagnetic spectrum. But at first, we end up getting that red that we would expect. And as we turn up the temperatures and get closer and closer to temperatures around the sun, then we get this graph that continues to increase as we go to higher and higher frequencies. These are lower and lower wavelengths, so higher frequencies. But then there's this weird drop off. And this is the part that Max Planck stepped in and ended up solving.
So what happened was this guy came along, and his name was Max Planck, and he tried to resolve this. This was actually called the ultraviolet catastrophe, because in the ultraviolet part of the spectrum, the formula didn't work. And what he did was he came up with a new formula, and that formula matched this graph. So for Max Planck to be able to derive this formula, he comes up with this new idea. And the new idea is based off of how atoms are producing this energy. Now, we know that when it's cold, it's a black object, a black body. It's absorbing all the frequencies. And when it gets hot, it starts to emit them. But how is it emitting them? He says that the energy is being emitted in discrete amounts. Now, what does that mean, discrete amounts? It just means in bits or chunks. So you can have a little bit, or you can have double that bit or triple that bit. Each of these chunks don't have any value that's in between here. And if you look at his formula, energy of the photon, we're going to learn about this with Einstein and the photoelectric effect, is equal to NHF. So what this N was a whole number. So he said you could have this energy of Planck's constant times the frequency, but that it had to be in a whole number ratio. So you could have 1 of this, or 2 times this, or 3 times this, but you couldn't have 2.6. You couldn't have 3.7. It's kind of like money. You can only have a penny, or 2 pennies, or 3 pennies. You can't have 3.2 pennies. The smallest amount is a whole number. So this number he comes up with, is called Planck's constant. And we'll come back to this when we practice this formula and put the numbers in. And F is obviously the frequency. So another way to visualize this whole thing is that energy was originally thought of more like a ramp. So if you're a person, you can walk up the ramp and you could stand anywhere on this ramp. And that's the way energy was thought of. But what Planck was saying is that energy is more like a staircase. So you can stand on the ground, you could stand on this stair, you could stand on this stair, but you can't stand levitating in between those. So the energy that you can have has to be equal to this multiple of 1, 2, 3, 4 as a multiple of the number of steps that you can't stand on part of a step. So Planck comes up with this new crazy formula. And it's a mathematical formula that's really nice because it matches the curve. So he can throw the wavelength in there and a bunch of constants, and he matches the curve. This is based off of this idea of quanta. It's a quantity. It's a fixed amount that is you can think of it as a whole number of a small bit. And this bit idea is called quantized energy. But the problem is he makes this crazy mathematical formula, but he still doesn't understand why this formula is working, even though it does match the data. So here's what the problem is. He's still trying to understand classical mechanics. And classical mechanics says that the energy that this light has, or any electromagnetic wave, is based on the brightness. Now, if you remember from the waves unit, that's amplitude. So when we said we looked at this value from the equilibrium, that was the amplitude, that was the energy of the wave. But all of a sudden, something different is happening. Now in modern physics, we're seeing that that energy is actually proportional to the frequency. So we have this disagreement between these two ideas. And it was Albert Einstein who resolved this problem by explaining the photoelectric effect, an experiment that I'll explain next. So the photoelectric effect works like this. We have two metal plates connected with wires to a power supply. So all this is a little metal plate. There's a negative charge pushing on this, so we know that this is negative. And on this side, we know that this plate is positive. And if you do this in a dark room, nothing happens. You don't get any reading in the ammeter. But what they tried doing was first putting low frequency light, shining this low frequency light onto this metal plate. Now, they first tried, let's say, red. Okay, so they put red on there and nothing happens. So what they expect to have happen is if they turn up the amplitude, if they make the light brighter, it'll have more energy and knock the electrons off, and they'll start to flow, and we'll get a reading in the ammeter. But it didn't happen. When this got brighter, no electrons came off at all. But then they found, so we have dim red light doing nothing, bright red light doing nothing. Then they tried blue light. So now they try low frequency or high frequency blue light at a low amplitude. So not much. It's not very bright, but it's a higher frequency light. And they notice that some electrons start to come off, but not many. So they get a current flow down here. But then when they turn up the amplitude, more electrons start to flow across. So the brighter blue light is now knocking off lots of electrons. So let's look at the expectation. That brighter light, greater amplitude, would make more electrons flow. But the observation was that low frequency light did nothing, even when it was at a high amplitude. However, high frequency light made the electrons flow. But if there wasn't much of it, not much was flowing. But brighter light at a high frequency meant lots of electrons were flowing. So it was Albert Einstein who was able to explain what was happening, and this is what he won the Nobel Prize for. So what he said was that there were these things called photons. They're wave packets. And every time you turn on the light, if you have red light, you have this packet, and it's got low frequency, so therefore it has low energy. So now he's saying that the energy, just like Planck, is too low to knock off an electron. Even if we put lots of them, it doesn't help anything because there's not enough energy to knock the electrons off. But then he says if we get the photons to have a high enough frequency, then they can knock them off. So let's say we have very dim blue light. Very dim blue light would be not a lot of photons. If we shoot one photon across, that's going to make one electron go off. If we make the light brighter, that just means there's more of these photons, which means more electrons can be knocked off. So light is acting not as a wave, but it's acting as a particle that has a particular wavelength or frequency. And these wave packets are known as photons. So now we have even another experiment. So hang in there because all of this stuff comes together and ends up painting a picture of the modern atom. So the way the Compton effect works is we have an electron. This is an experiment that was done. We have an electron that's just sitting still, and it gets hit by a high frequency photon. So we could say, let's say this is blue light. So we have a blue photon. This photon is Einstein's idea of a wave packet. And when the photon hits the electron moves off. So we see this electron end up in a new location, and the photon goes glancing off, and now you can have a detector here that detects the color, and the color is lower frequency. So maybe it came in as blue and it went out as red. So what does that tell us? It says that this electron picked up energy. It picked up momentum. So all of a sudden this electron gained MV and it gained KE. Well, where did it get that energy from? Well, it must have come from the photon. So where's the lost energy? The lost energy is in the fact that this has a lower frequency. So now Compton showed us that this photon has less momentum, less kinetic energy, and here it had higher. In other words, photons have momentum and energy. So we can look at it as a conservation law. Here is our first photon that's cruising along. We can say that the energy of that photon then turns into the kinetic energy of the electron, and the lost energy is the energy of the photon after the collision. And the same thing is true of the momentum of the photon. The momentum of the photon initial is our total momentum. The electron gains momentum, and the momentum of the photon after the collision decreases. So we haven't learned this formula yet, but what Compton did was he said from Einstein, E equals mc squared, and we'll get into the details of that formula later. And we know that from Planck, E equals hf, that we could take one of these c's, c is the speed of light, and bring it over here and say that v, the c of the incoming photon, of the incoming photon is v, and that gives us a formula of hf over c. And we know that mv is momentum. So now we have a formula for the momentum of a photon. So what are photons acting like? Well, these little wave packets are acting as particles, and that's important. We'll see in a minute. And so what we're saying is as frequency goes up, then the momentum of this photon also goes up. So all of these experiments started to bring up a fundamental question, which is light, which remember we're talking about all electromagnetic waves. Is light a particle or is it a wave? Because we have a lot of experiments that show light acting as a wave. Remember polarization in the waves unit. Light acts as a wave, and we could filter out that wave. If light was a particle and we had a filter like this, it wouldn't get filtered out. All the little particles could just make it through. So we know that light's behaving like a wave. And diffraction interference, when two waves hit each other, they make a bigger wave or they cancel out to make a smaller wave. That shows light behaving like a wave. And finally, Maxwell's theory, that was the theory that showed us that light is an oscillating electric field and magnetic field. So there's some strong evidence that light is behaving like a wave. In the particle theory, Isaac Newton came up with the corpuscular theory, which he just said that light was made of particles, but he had no reason for it. So there's no evidence for this. However, Einstein, with the photoelectric effect, showed photons knocking electrons off. So they weren't passing through like you would expect a wave. They were hitting it like a particle. And the same thing with Compton. Compton had these photons hitting electrons and making them move just like a particle, not passing through them. So how is this possible? How could you have these different experiments, but we know that light has to be one or the other? Well, Bohr came up with the theory of complementarity. And I feel like the best way that I can explain this is with a little diagram that looks like this. Imagine that we have a box. And in this box, we don't know what's inside. We can't look down through the top of the box. But we do have two little windows that we can look in. And in the one window, we open it, we see ears, and we see whiskers, and we see what looks to be the top part of a rabbit. But then in the bottom part, we open a little door, and we can see the scales of a snake and the skin of a snake. So what is in the box? Well, it's kind of like this. We have our wave theory where we're doing experiments where we say, oh, we have all these experiments. It must be a wave because it's behaving like a wave. And then we have, no, it must be a particle because we have experiments like this. Well, it's like the one group is saying it's a rabbit and the other says it's a snake. Well, it's not. It can't. It has to be this combination of exhibiting both behaviors at the same time. So maybe it's not a snake or a rabbit. Maybe it's a snabbit. And that's the idea that Niels Bohr came up with. And this was the idea of complementarity. And what he said was that we could have experiments that show us one characteristic of a phenomenon and another experiment that shows us a different characteristics of this phenomenon, but that both are correct. Both are giving us a picture of this thing that we don't really have a full idea of what it is. We can only understand as much as our experiments show us. So let's bring it back to the models of the atom. So we said that Rutherford, this was the best model we've gone over so far. It's the planetary model where we have, this is acting like the sun, this is a planet, and it's orbiting. But there's a problem with this because remember that anything that's in orbit is changing direction. And if it's changing direction, it is accelerating. And if you remember from the electricity unit, that accelerating charges emit light, okay, or an electromagnetic wave. So here's a problem. Atoms aren't just constantly emitting light. We don't have everything in our homes just doesn't glow. And not to mention, if it was emitting light, it would be losing energy and it would end up eventually spiraling into the nucleus, so you wouldn't be able to have matter. So it's a good model, but it's got problems. So Bohr came along with an explanation for this. And this is the Bohr model. And what he said is maybe the electrons aren't orbiting, maybe they're hanging out in different levels. So they're in these, if you learn in chemistry, the idea of shells. So they're sort of hanging out in these different positions from the nucleus. And what he said is that the electrons can jump. They can jump between levels. So they can jump down a level or they could jump up a level. But just like the quantization idea, they can't go halfway. They can't go 2/3 of the way. They have to go either from one level to another. Now, they could jump 2 levels or they could jump 3 levels, but they have to go level to level. And the reason they have to go to level is because the energy has to be a fixed amount. So we'll get into how you can solve those problems soon, but let's look at this. When they jump down, this is super, super important. When they jump down, they emit a photon. So you can think of it as losing energy as it jumps down. But if it loses energy, it must conserve energy. So you must get something for that loss of energy. So what does it do? It kicks off a photon. The bigger the jump, the more energy lost, the higher the frequency of the photon. And then also they can jump up, but to jump up, they must absorb a photon. So this has to absorb a photon of a particular frequency, and if it does, it will jump up a level. So to understand Bohr, we need to understand Max Planck. Because remember that Max Planck ended up getting this formula for this curve, for the blackbody radiation, but it was based off of this idea of E equals hf, and if you remember, we said NHF with specific whole numbers. So if we have an electron, electrons can only exist at certain energy levels. They cannot exist halfway in between. So the electron either has to absorb a photon to go up or emit a photon to go down, but otherwise it's just going to sit in its level. And the formula for this, if you remember, is E equals HF, which is on the reference table, and that's equal to hc over lambda. And on the reference table it says E photon, and now we know why that is, because that's the energy of that wave packet that Einstein explained. Now the problem with this is we have a little tricky bit we have to know. The unit for this is joules or electron volts. So joules are for big things, and because we're dealing with small things, they came up with a new unit called the electron volt. And the electron volt is 1 eV, and that's equal to 1.6 times 10 to the minus 19th joules. Now you have to be very careful here. Electron volt, it sounds like voltage. This is a unit of energy. That's very, very important. So what is an electron volt? It's the energy needed to move an electron through a potential difference of 1 volt. That's all it is. Okay, just for this unit, just remember electron volt is a unit of energy. So let's do a quick little problem. How many EVs are there in 5 joules? So we can just do this as a conversion. We can say the energy we have is 5 joules, and then we can multiply that by 1 EV is 1.6 times 10 to the minus 19th joules. So we multiply the 5, divide by this, and you end up with 3.125 times 10 to the minus 19th what? Electron volts. That is the energy. So let's put some numbers in and actually do some real problems that you might get on a test. So the question says, how much energy does a green photon of frequency 5.8 times 10 to the 14th hertz have in joules and EVs? So the way we're going to do that is with E equals HF, and we know that H is 6.63 times 10 to the minus 34th joules seconds. And you don't have to memorize that number. It is on the reference table as Planck's constant. And we're going to multiply that by the frequency, which is 5.8 times 10 to the 14th hertz. And that number comes out to 3.85 times 10 to the minus 19th joules. So the next question was to do it in EVs. So in EVs, that's basically just a conversion. So that's going to be the energy is equal to 3.85 times 10 to the minus 19th joules. Oops, joules. And we know that 1 EV is 1.6 times 10 to the minus 19th joules. Multiplying, dividing, that gives us an answer of 2.4 EVs. And you can see why EV is a very convenient unit, because it gives us numbers that we can get our heads around a little bit easier. So now let's do this problem in reverse, and this is a very common question to get asked. It says, what color is a wave of energy 4.77 times 10 to the minus 19th joules? So basically we're going to do this in reverse. So this time we're given the energy, and we're going to put in Planck's constant for h, and we're going to solve for f, the frequency. So that's going to come out as 7.2 times 10 to the 14th hertz. And we can look that up on our chart. So for light, we said 7.2 times 10 to the 14th. So that's going to put us right in here, 7.2. So the answer is violet light. But pay attention, because if they had given us a question like that and the number did not fall in this range, let's say the number came out higher than this. Well, what's higher than violet? The answer would be ultraviolet. And if it didn't fall in this range and it came out below this number, that would be infrared. So you do E equals HF to get the frequency. You can look up the color, but if it's above violet, it's ultra. And if it's below red, it's infra. We're going to go much more into how to solve Bohr problems in the next video, but the last thing you need to know about is this relationship of E equals HF and what it would look like as a graph. So we know that the change in Y over change in X is the slope. So let's divide frequency over to the other side so that we have this. Now we have our change in Y over change in X. That's equal to slope. So what's the slope? The slope of this line is Planck's constant. So if they ask you to solve for that, you should end up getting 6.63 times 10 to the minus 34th joule seconds.